All right, well, I want to thank our sponsor for today, Build Equinox. Build Equinox manufactures the CERV smart ventilation system in central Illinois at its 100% powered facility, which is being verified as a zero energy capable facility over the last year. This serves as the first smart ventilation system for residents with active monitoring and control of indoor air quality, measuring carbon dioxide and total volatile organic compounds, VOCs. With the Serve's IAQ sensors, filtered fresh air is delivered to your client's home when they need it most. The Serve saves energy with its efficient heat pump energy exchange technology. Not only that, but this allows the Serve to actively heat or cool and dehumidify incoming fresh air. This makes Serve ideal for any climate, whether hot, humid, or cold. Serve Ice connects the Serve online, making it even smarter. This enables online monitoring and control of the Serve from any internet-connected device and provides information on the home's indoor air quality impact on occupant health and cognitive sleep. Don't just ventilate your client's home. Make sure their house is a healthy home with the CERV Smart Ventilation. All right, well, welcome everybody to 7 steps for designing an economical net zero home. This course is approved for 1 hour in continuing education units, GBCI, AIBD, NARI Green, Certified GreenHome Professional, Certified GreenHome Professional, and is also approved for AIA, Health, Welfare, and Safety. This course may also be applicable to your local design contractor state license. Today I'll be your moderator. My name is Brett Little, and I am the Executive Director here at the GreenHome Institute. GreenHome Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. I'm really excited about this course today. Net zero energy design, construction, renovation is a growing trend. By 2050, the world wants to be a net positive world, right? So every individual building, house needs to start thinking about how it can get close to zero. And just for your own, clients' needs, that's obviously reducing their costs. From a low-income housing tenant application, that's what we call the concept of new affordability, where people more and more these days have less and less resources, and so having no bills whatsoever can benefit everybody. And so we're real excited to continue our 2-year zero energy series, zero energy capable series, and excited to give you new tools, new ideas, new resources to accomplish that. So with us today as our presenter is Ty Newell. Ty is co-owner and co-founder of Build Equinox, which manufactures the CRV Smart Ventilation System. He retired from the University of Illinois as an assistant dean in the College of Engineering, having advised 70 master's and doctoral graduate students. He is an emeritus professor of mechanical engineering, and he has lectured around the world on indoor air quality, comfort, solar energy, building energy efficiency, and resource conservation, including many international keynote addresses. Ty lives in a 100% solar-powered home that includes automated fresh air control, rainwater harvesting, and he works in a building that is located in a 450 square foot facility in Urbana, Illinois, that is also 100% solar-powered. So with that, Ty, I'll hand it over to you.
Thank you very much, Brett. Thank you for hosting this, and thank you to all of those out there who are taking the time to participate in this webinar. And I look forward to interacting with you and answering your questions. Let me see if I can kick up a laser pointer. The house that you're looking at, we're going to be talking about a house somewhat like that, and then how it's different from, say, a more conventional house. And surprisingly, there's really not too much that's different. And so we'll be looking at that from various viewpoints, not just energy, but the economics, the financing, and other aspects as well. This is my house, what we call Equinox House. We built it in 2010. There's no ifs, ands, buts about it. It's a 0+ house. It has been from the day it was born. The solar collectors in the background, we'll talk a little about. That's 8.2 kilowatt solar array, but it fully powers the house. Plus it has an additional 2,000 kilowatt hours a year that are used for our electric cars, a Ford Focus EV, fully battery-powered car that we put about 6,000 miles on per year, and then a Ford C-Max, a plug-in hybrid that we do an additional couple thousand miles a year. So I'm just pinching myself these days that where I live, and as Brett mentioned, where I work, where I'm talking to you from in central Illinois, is fully solar powered, and then a large fraction of our driving is also economically solar powered. And that's the topic for today. As far as ourselves, Brett gave you quite a bit of background. Build Equinox, our primary activity revolves around smart ventilation. So what a number of people are calling beyond energy now, as so many people are building net zero and zero plus homes. And so we build this smart ventilator we call a SERV, which automatically manages excellent air quality in a home. But really our guiding mission, Ben, who's our president, myself, and then Alex Long, the co-owners of Build Equinox, we're really trying to see how to develop solutions for living sustainably, how to live on our daily allowance of solar energy, and in the words of Aldo Leopold, how do we live on a piece of land without spoiling it? So that's what gets us up every day and motivates us to do our best to help make this real. So we put a fair amount of our effort into research, both for our own developments as well as for helping to educate others. And on our website, you can find quite a bit of information from other webinars and our newsletter. But this report that's shown, Vermont report, this report is one of the most detailed reports that I know of after almost 50 years of research in this, in housing and energy, that looks at a series of homes and really helps show the differences in energy that different people need and want among 13 identical manufactured homes in a very challenging climate in Vermont. And you can download that from our website, and I encourage you to do so if you'd like to have a lot more depth as far as actual energy usage along with comfort and air quality in homes. A brief history of house energy. We are really in this area right now, homes that are built without much effort other than what codes would typically end up moving people to build, versus what you might think of as the ultimate level in house performance, but economical level, that we're in this area. And you can see relative to where we were about a century ago, this house, which if it had a utility bill would be paying about $15,000 a year, would use an enormous amount of energy to stay comfortable. But this house, which would use, say, 150,000 kilowatt hours of energy, the blue for climate conditioning in our lovely Midwestern climate here in Illinois, and then the orange showing the people energy, the electrical energy for cooking, TVs, lights, other things we'd like to do. And over the years, as we concentrated on adding storm windows, some level of insulation in the structure of the building between the studs and up in the rafters, sealing it up a bit better, moving from about 30 air changes per hour with a blower door test at 50 pascals to about 10. And then continued efforts from 1950 to 2010 as energy costs made it economical to think about improved insulation, additional insulation and sealing, improvement in windows, and getting us now to what, without much effort in standard construction practices, would be, say, a blower door leakage of about 6 air changes per hour, to a level that as many people are working toward building, say the passive house level, whether the European or the North American FIAS group, of much reduced air changes per hour. But situation which, as you reach this level, as you drop below 6 air changes per hour, people are going to tell you your house smells, and you'll be using ventilation, hopefully for your health as the primary reason, but also to keep odors down in your house. But you can see that as we go to these high levels of insulation and avoid thermal bridging and go to very high performance windows, that there's really not too much of a difference in energy, maybe dropping from about 20,000 kilowatt hours, if this were an all-electric house with modern heat pumps, to about 8,000 to 10,000 kilowatt hours like Equinox house, with a house with 2 to 4 people in it in a challenging climate. The other thing we see is that this orange, the people-related loads for cooking, lights, TVs, computers, this has grown over the years, although it's now reduced again with efficient LED lighting, efficient televisions, and things of that sort. But now we're in a house where human loads dominate the loads over climate. Just like a car in the 1950s at 2 tons of metal, it didn't even know people were riding in it, to today's more modern and more efficient vehicles that the more people that you add to the car, you will have a noticeable impact on mileage. Now, one thing I wanted to mention over here was that in the 1920s, this was like Miss Ruby's house where I took piano lessons back in Southwest Missouri. She didn't keep this house comfortable. She kept the parlor comfortable where the piano was, and my first job when I arrived for piano lessons was to go out back to the coal pile, put a couple of chunks in her fireplace to keep the parlor warm, but the rest of the house was freezing cold. And then as we moved to this era, this is really the start of when we started keeping the whole house comfortable. And now, for sure, we're quite good at keeping the house comfortable, but where we've fallen is that we have not kept people healthy. We have seen significant growth, of more than doubling of respiratory illnesses, prevalence of asthma in the modern homes. And we need to get back to thinking of a healthy home. And this slide, and this will be the only one where we're talking about health, but you can see more of this type of information from our website online. If we make a plot of the infiltration leakage characteristics of homes, this is from Lawrence Berkeley Labs data, and you'll find the references for this on our website. But from the 1920s, assuming a baseline of a 1894 house, and you look at the ratio of particulates, dust particles inside the house, to what that used to be back in the 1890s, as we sealed our homes up, and not only dust particles, but this is also volatile organic compounds and carbon dioxide. And carbon dioxide, from more recent research, is now shown to be something that definitively impairs our cognition. And in a serious enough manner, there's a lot of dollars associated with that decline of cognition in our homes and buildings. But we see that asthma, and this is data from 2 different sources, CDC and National Center for Healthy Homes, but they pretty well lay on top of each other. We've increased from a level of maybe 3% or so asthma prevalence to where we are today, going up to 8 to 10% asthma, depending on where you live in the country. Northern climates, asthma prevalence is higher than in, say, southern climates, where homes are better sealed and you're staying in a home longer during inclement weather. And we see that the increased concentration, as we've sealed our homes up, that this has grown, and these 2 things really map quite well on top of each other. To give you an idea how these costs correspond, before we get into the nitty-gritty of a single house, if all homes were sealed with modern construction techniques and all electric high performance heat pump water heaters, heat pump heating and cooling systems, we would be spending about $160 billion per year to keep our homes comfortable and to allow people to do all the things we'd like to do in our homes. The cost of influenza, which is impacted by the fresh air in our homes, is about $90 billion a year. The cost of colds is about $40 billion per year. The cost of asthma is about $60 billion per year. 1 in every 3 to 4 homes has someone with a severe respiratory sensitivity. And you add these up and you find that, you know, these things that we can do something about, these things are exceeding where the cost for energy will be and are quite comparable to what our current energy costs are for housing. And then when we look at our productivity, our ability to think, and we put a dollar level on that based on our diminished cognition, which is about 5 to 10% with what typical carbon dioxide levels are in a home, that we're losing over $1 trillion a year in productivity capability at home and at work and at school. Well, let's look into the nitty-gritty of how to design a home. And in designing a home, it is complicated. And it's simultaneous. So as you choose this window, you're going to impact the heating, the cooling, you're going to impact the insulation characteristics of the house, and you'll impact how the appliances impact your comfort. It's all interconnected, and it is incredibly complex as you put together the economics and the finances, what Brett was talking about, together with the performance. And so how do you find which way to go and how to begin this process? Among other things, it's important to not solely concentrate on form and not solely concentrate on function, but integrate the two. And Equinox House is an example, at least to me, of where we've done our best to integrate both form and function. This dumpster that I found in Asheville, North Carolina, it's the best looking dumpster I've ever seen. And it, to me, shows at least in the dumpster world, just the ideal for combining the two. In terms of our house, this simple shed roof on the front and on the back, as Brett mentioned, we harvest rainwater. And this rainwater harvesting for our house is designed for 80% of our water needs. Currently, we're approved by the State Department of Public Health to supply rainwater for toilets, which is about 40% of our indoor water needs, and for gardens. And so roughly about half of our water needs are supplied by rainwater. And so looking at the roof, it's more complex than it seems because this uplifted, what we call the equinox overhang, as we've just gone through the fall equinox, the sun has now lowered in elevation to where it can see these clear story windows, and this uplifting overhang, reflective overhang, concentrates solar radiation into our house during the winter, and this 212 pitch on the lower overhang similarly reflects light during the winter into the house. But then during the higher solar altitude angles in the summer, we reflect off and go back into space, and we totally cover. And you can see the similar overhang on these windows during the summer period. So we don't have that additional air conditioning load, which is substantial. But, you know, is this house a chicken coop or a Porsche? I've heard it described as both. And that's kind of the nature of the qualitative aspects of design. But I would note that Deb and I both love modern design. As flawed as Frank Lloyd Wright was as a person, we like his ideas. In our case, what we consider a modern Usonian home, that open public space and enclosed in private space, that somewhat hidden doorway going in, organic architecture with simple materials like rock, stone, glass, metal, wood, and these have a benefit of not off-gassing as many materials do. And so we had the pleasure of having Gene Ascoli as an architect who has a lineage of formerly being an architect with Taliesin Associated Architects, Frank Lloyd Wright's firm. And we just love the design. But our house, floor plan of it, we were monitoring a series of homes in the development that we live in for the developer. And it's really the same floor plan as many of our neighboring homes. We just put a different looking shell on it. And then we knew how to make this a high performance shell, how to insulate and seal it properly. And that's really the main difference, along with doing some sensible things on the windows, so we could get the daylight, so we could get the view that we would like to have. And otherwise, it's not much different. So these 7 steps, even though there's this simultaneous interaction among the different elements of a house, we can take a pathway through this design and I think make things easier. And so if you follow this pathway, and we'll follow through the energy performance, the economics, the heating and cooling and dehumidification, humidification characteristics of these changes, that these will, I think, give you some perspective of, say, a home without any windows versus a home with a lot of windows. And then following through from this so-called conventional home to one that's very well sealed, say passive house level of sealing, to adding a heat pump water heater. And without going into the details of it, the simple change from an electric water heater, whether an instantaneous or a tank type, to the new hybrid water heaters, is enough savings in energy for a family of 3 to 4 that it will give you about 6,000 to 8,000 miles of electric vehicle driving. And similarly, a change to a modern heat pump clothes dryer is an additional 2,000 to 3,000 miles worth of driving in an electric car. And so the interdependence among these different design elements in a home, optimal insulation, solar energy, and then finally transportation. As we move through these steps, this is what takes us from being a home that is not just simply a conventional home with its cost, but one that has superior performance along with superior economics and superior finance. The monthly cost will be less. And this is what you need to go to the banker to help finance a bit higher upfront costs. Let me just state about windows. What you will find as you move through any economic analysis, if you apply the proper economics, lifecycle costing, for example, is that you'll find that windows generally don't pay for themselves, that the energy value of windows usually will not pay, and I can't think of a case where it does, but as an academic, I always like to qualify things. But more than likely, you will find that the cost of a window will not be paid for in terms of its energy performance. And more often than not, for example, a north-facing window or a window in the southern tier region of the U.S., it always has a penalty. It always adds, say, additional air conditioning load, comfort conditioning energy. But this house, which I just happened to find, who's going to buy that house? Yeah, maybe there's one other person besides the person that owns that would buy that house, but we do like windows. We like daylight. Our eyes are naturally tuned to daylight, and we like to see beautiful surroundings, from oceans and lakes to whatever our gardens may look like. And the aesthetics are important so that a house will be marketable. But that is really the essence of windows. They're among the most complex, if not most complex, elements of house design. And so what we recommend to folks is that they look at windows from the viewpoint of the aesthetics, from the location they're in, and then whether or not the economics for achieving that level of aesthetics is worthwhile. I'm going to mention Zeros, which is software that Build Equinox has developed. It actually has a pretty long lineage, and I'm not going to go into the details, but you can sign up for free. It's free to use online software, and it is design software. Its purpose in life is to save us time, to save you time, in helping to look at the economics, the energy performance, the moisture performance, the air quality performance, as opposed to, say, certification software, software that in various manners you're probably more familiar with, but ones that keep telling you, don't do this, you didn't make this goal. This isn't telling you any of that. It's simply saying, you know, if you double the size of the windows or you go to this type of insulation, here's the cost impact, here's the energy impact. You decide if that's the right way to go. If you go to this website and sign up for it, it's just there for you to use. I use it with classes at the University of Illinois regularly. These materials that are posted online are the materials I use with these graduate classes in sustainability, where they do house design projects using Zeros. And we're not going to bother you. You know, this isn't for getting your name on a list or trying to sell you something or selling your information to someone. We're not doing that. So, so you can sign up and you'll find a lot more detail for these 7 steps buried within these write-ups and then files that you can load into Zeros for looking at all the data that we're going to talk about today. The purpose of Zeros, it's simple software to use, and it is meant to save time. Your time will be better spent on a project making sure the right things are ordered, that they're delivered to a project site on time, that they're getting installed with quality and in the manner they should, than sitting at a computer and getting another decimal point of energy performance. You have a crew of 7 show up at a site, but the material's not there. You're still going to pay the crew, and that's probably going to be a year's worth of energy costs in these high-performance homes. You've got a lot better use of your time than sitting at the computer, and this is meant to help streamline that so you can get through, get the information you need, and then put the detail into where the utilities run in the house, rather than a helter-skelter fight between the plumber and the electricians and the HVAC folks to get the best runs. So that's the reason and meaning behind it. And then to put in powerful tools so you can see what's happening economically and financially. Maybe the house is economical, but if it makes your monthly payment something that you're not going to be able to afford, that's important to address. And how much moisture do you need to take out? Do you need to take out 5 liters a day, or do you need to take out 50 liters per day of water? This is a feature that you typically won't find in many design programs. This is heavily validated. So while you won't find it certified, and that's because, you know, we developed it for our own use, but have now made it available for others to use. We have vetted this through BEST tests, a national test formulated by DOE. And BEST test basically is a simulation of a number of home variations using what are considered the gold standard for building simulations. Those of you who have been long enough would recognize DOE2 and BLAST, as well as Seri Sun Code. And DOE2 and BLAST are now Energy Plus, but BEST test was formulated with these models. And to see the detailed validation information, if you go to Luis Martinez's doctoral dissertation, He was my last doctoral student, and as Louise says, I left the best for last, but he was a wonderful, wonderful graduate student, but I was somebody who was very fortunate to have many among the 70 graduate students that I had the pleasure of working with. But anyway, you'll find more than enough information on the validation, the computational validation of zeros, as well as if you are somebody who's having trouble getting to sleep, something that could help on that end. Experimentally, empirically, we've also validated and vetted zeros with a number of different homes. And this scatter plot, which shows outdoor temperature and then daily energy usage in kilowatt hours per day, all of these solid data points are from this Vermont report, so you can find the details of it. But it's the energy per day of 13 identical homes with very non-identical people living in them. And the zero simulation for these homes, if the home had one person, are these lower yellow points. And if it had three people, people are important in these homes. And the difference between one person and three people, if they're average people, and again, average people don't exist, that this is where the homes would perform. But these homes, 1,000 square foot homes, all ostensibly manufactured with identical practices and materials, what's happening in homes up here versus these people who barely seem to breathe or move in their homes? This variation is real. And if you're a home builder and you design a home that is to this performance, you're going to have a lot of callbacks because half the people are up here and half the people are down here. And this half is going to call you because the home's not performing well. And unless you can certify that a person's going to live an average life, you will need to be able to handle this type of variation, which these homes do very nicely. To add some perspective, when we look at conventional homes, as I described, these are data points from modern conventional homes. You can see how conventional homes use significantly more energy per day than homes that are in this range. Equinox House also layers right along in here, and you'll find modern high performance homes in this kind of range. So as we talk about 1 or 2 kilowatt hours per day, and that looks like quite a big difference here, when we go up to what is more representative of current modern housing stock, it's not that big of a difference, but still we want to make these homes as best as we can. I'm not going to go into the details of using zeros. You can find that out in those handouts. But when you load zeros up, you'll see a dashboard that looks something like this. For example, this page shows how to put in number of people, the location, and there's over 300 locations in here, including China, Europe, Canada, Mexico. So whether you're in Wuhan, China, Aachen, Germany, or Urbana, Illinois, you should be able to find a weather location that's similar to where you are. And then simple parameters to add in. This dashboard shows you where you're going to find other information, like on solar energy and economics and finance, parameters that you add in as far as the interest rate on a mortgage, the real estate taxes, the cost of a window per square foot, the cost of a heating and cooling system. And so you can find that detail in there. And if you go to the project section, that's where you can see to export as well as import cases. So some of the folks we're working with projects around the country, as they design a house, sometimes they'll export their project or case file, and then they'll email it to us, and then we can load it in and then take a look at parameters to see if they're okay. And then similarly, you can import. So these 7 cases from those files on our website, you can import. And when those are imported, this is just what they look like. And I won't spend any time going over that. If you go to the overview, this overview page has a lot of information, and this is where the data, which the remaining portion of this talk will be covering, this is where that data is largely coming from. Some of it's also put in more detail in economics and finance and solar, but for the most part, the life cycle cost comes from here, the total energy usage, here's the design day information for a particular location. And for these 7 steps, we will use Urbana, Illinois, because we are one of the lousiest climatic regions of the country. We have both a heavy, hot and humid summer conditioning load, as well as good Arctic blasts during the winter for a good cooling load. And down here, you can see what the design day conditions would result in as far as heating and cooling capacity. And we'll take a closer look at that. And here's the design day latent conditions. How many kilowatt hours of capacity would be needed, and what that means as far as liters per day that you're either vaporizing if you need to add humidity to the air or dehumidifying. And there's also air quality. How much airflow, both from infiltration or leakage versus what's coming in through some type of fresh air system. So with zeros, you can put in our Serve smart ventilation system along with an HRV or an ERV, and zeros accurately models moisture and latent conditioning. We have experimentally validated that over multiple seasons, that we are accurately predicting how much moisture is added or taken out of the air over the course of a year. But this will take the impact of whether there's moisture transfer or not within it. And then this summarized information on energy loads, but then all along here, even more detail on a monthly basis of the thermal energy, the latent energy, the electric energy that's coursing through the different elements of a home. So lots of information, simple to use, and hopefully simple to understand software, but a lot of information going on. Let me point out one other feature. In optimization, this life cycle sensitivity, these arrows are what help you navigate, figure out which way is up. So this down pointing green arrow with a $sign or a leaf tells you if life cycle cost is going down as you increase wall thickness and energy is going down. And almost always, but not always, as you increase insulation, the energy will go down. But at some point, the value of adding additional insulation drives the life cycle cost up rather than down. And so it lets you see both economically as well as energy-wise which way is up and down. Here you can see, for example, a south window relative to the economics that I have put in for windows, that it's going to drive the life cycle cost up, even though at this point it would have a benefit as far as annual energy. Now, this house has no windows in it. Case 1 is a windowless house, or one extreme example. And as you add enough windows, you will find at some point, typically by the time you reach 10% floor area in south-facing window area, that this arrow will start to go up as well as the cost. And you can see for the solar economics that both of these are going down. It's a new world. Solar panels cost less per square foot than windows, than high performance windows. And the economics are saying, incorporate solar in. Your life cycle costs and energy will be benefiting. So that's the type of information, and these next slides now will take us through these results. And you really need to look at the details within zeros and start using it to get familiarity. So, grab a cup of coffee and navigate around and try these things out. But what I hope this convinces you is that zeros will let you see in a very simple manner which way is up, economically and energetically. So from our case 1 and case 2, which are conventional homes, but case 1 is a 2,000 square foot home, typical insulation, about 6-inch of wall insulation and about 12-inch of below and attic insulation, but a 2,000 square foot ranch located in Urbana with 3 occupants. And here's that same house, basically a 50-foot by 40-foot floor plan. But now with all the south facade, about 25% of the wall area with south-facing windows, good Energy Star south-facing windows. And you can see that by having the whole south facade with windows, there's not a huge energy difference. Now, when we get to cost, we'll see there is a large cost. Now, the rest of these cases are all the windowless case. And the idea here is that, okay, here's extreme 25% floor area with windows, and here's absolutely no windows. And so 10% floor area of windows, which is, it's a good target to shoot for. That gives you lots of daylight, gives you reasonable solar input if you'd like to have that. But more importantly, it's more than enough for you to get the view of your gardens, of lakes, of mountains. And Equinox House, for example, has 10% windows. So we have about 200 square feet of windows with 2,100 square feet of floor space. And interestingly enough, half of those windows are on the north side. So those clear stories and then small egress windows from bedrooms you saw in the picture, that's about half of the window area, and the other 100 square feet's on the north. And it's on the north because that's where our gardens are, and then north-facing window daylighting is just wonderful light to read in and to work in. And it's a high-performance zero-plus house, so the software will let you analyze that. But if we go from this house to a house that now is sealed, so going from 6 ACH, what conventional housing construction would typically result in, to 0.6 ACH, but now with a smart ventilator assumed, you'd see that you would drop about 1,500 kilowatt hours per year just by that change. If we then add in a heat pump water heater, and the heat pump water heater next to climatic and ventilation energies is your next major source of energy within a home. The heat pump water heater or hybrid water heater has a dual benefit of helping to cool you in the summer, and its cooling advantage of the summer in all climatic conditions in the U.S. outweighs its cooling detriment in the winter impact on the home. And this is how that annual summary, it's again another 1,000 to 2,000 kilowatt hours a year, depending on the number of people in it. So another substantial drop of annual energy. And then this final case, as far as what we'll do to a house, that will go from what conventional construction would do to more economically optimal construction. And in the case of this house, this is basically taking about a 6-inch level of wall insulation, and economically for our region, that would change it to about a 10 to 12-inch thick wall, along with a little bit more up in the attic, but somewhere in the range of about an R50 for an attic insulation. Attic insulation is typically less expensive than wall insulation. That's why you put more up into an attic space than in a wall. And zeros will let you see that cost impact of the insulation relative to energy. The rest of these, as we move into solar powering the house, you see that the house doesn't change in energy, so we end up somewhere around 8,000 kilowatt hours a year, maybe about $800 to $1,000 worth of utility expense per year. Over here,
hey,
yes, Brett.
one quick question that came in is somebody was asking if you could just quick reiterate what the glass square footages on all sides are for each case.
Yes, yeah. So the 25% wall area, or roughly 25% wall to floor ratio. And as an old person, I'm trying to remember off the top of my head, you'll see it in that write-up, but it's about 400 to 500 square feet of south-facing window. And so, yeah, thank you very much for bringing that up. That's about 400 to 500 square foot of window area. And I think the assumed cost I have in which you'd have to look at the economic section is about $40 per square foot. So that would be about $16,000 to $20,000 worth of windows added to the house. And also in remembering, so that 400 to 500 square foot removes about that much wall area, and the insulated wall cost is somewhere in the range of I think $4 to $6 per square foot. And again, you'll find those cost details in those write-ups. But thank you for bringing that up. And any of those other details that that I've glossed over too much, let me know, and I'll address those. Over here are the solar cases, and we have two solar cases. And the reason for these two cases, which are the one case 6 kilowatt system and the other two cases a 9 kilowatt system, is that when I wrote this material up for the classes that I teach at the university, solar prices about 5-6 years ago were about $4.50 per watt. And with a 30% federal tax credit, about $3 a watt installed. But this other case reflecting more of today's installed costs of about $3 a watt that we're seeing around the country, that is with federal tax credit, a little more than $2 a watt installed cost, net cost. When we look at the economics, that's where we'll see a difference between the 6 kilowatt system at $4.50 to $3 a watt installed, and then a system that's about a 9 kilowatt system, an additional 3 kilowatts added for electric vehicle transportation, which has a very, very beneficial impact on the house economics, as we'll see.
And Ty, I just wanted to be sure that it's the 7 steps optimal handout that you're referencing?
Yes.
Perfect. Thank you.
Yep. Yeah, and Brett, also, if you wanted, you can take those PDFs off of our site, and you could make that available on your site as well, if there's a mechanism for you to do that.
Yep. Thank you.
Okay. On the house costs, the capital costs, what you're going to go to the bank and ask them for money to lend you. As Brett mentioned, a conventional house would be here. This would be a conventional house with no windows, and then adding in the range of 400 to 500 square feet of windows. And the reality is, I think most people use maybe 15% floor, window to floor area. That's from a study done by Washington State. But your house costs between these two extreme limits. Windows are a big impact on it. Here showing about, say, $25,000 for the cost that I have assumed within zeros. And so you can figure any of these with some level of window will add up some amount similar to the fraction of window that would be added to this no window case. And I've chosen then to use these other ones based on this no window case. So as we take a 6 ACH sealed home and move it to a 0.6, say passive house level, we're seeing an increased cost, and this increased cost, say $5,000 to $6,000, $7,000, $8,000, and that cost is due to them needing some type of ventilation system with efficient energy exchange. And so that's the main cost. Sealing a house is primarily labor and elbow grease, and you'll find those details on our site. But for sealing Equinox house, for example, taking it from a 6 ACH down below 0.6, that had a cost of about $500. Half of that was caulk and half of that was labor. As we change to a hybrid heat pump, that adds a few $100s on top of the cost of a regular electric water heater. We're not discussing gas. That's got a whole set of other discussions associated with it, but just an all-electric house. So that conversion doesn't add much to the house cost, but as we saw, the energy impact was quite significant. And then as we add more optimal insulation, that increases the wall cost by about $4 per square foot. And again, you'll see those dollar costs in the economic section of Zero. So all of that is discussed and included in that. As we add solar at a 6 kilowatt system at a $4.50 per square foot, we do see a significant increase in the capital costs. And at today's $3 a square foot rather than $3 per watt rather than $4.50 per watt, it's still an increase. And the main question is, what do the economics show as far as if that's beneficial to add on or not? And then how can you make this data real to the bank and to the appraisers so that they can see that it is a benefit, and it should appear as a benefit to them to loan you more money. Remember, loaning you more money is preventing you from writing a check that exports money out of your community to wherever your utility is located. This is money that's going into local construction industry to install it, and roughly half that cost is for that installation and balance of system costs. And you add another 3,000 watts to the 6,000 watt system, the cost will go up, and between the $4.50 a watt to $3 a watt would take you into somewhere in that range. As we look at your annual utility cost per year, here in case one and then case two, no windows versus windows, this is where we see how the utility, the energy consumption did drop with south-facing windows in this northern climate. In a more southern climate, that wouldn't be the case. But the dollar value associated with that is not that much. As we move toward a sealed home, a hybrid water heater, optimal insulation, and then finally adding solar, we see that we're dropping from nearly $2,000 per year for the utility costs, and that is typical of the utility costs from our field studies that all electric homes in our area are seeing, to a net zero solar powered house. The reason for this utility cost, assuming most people would stay grid tied, and we hope most people do, that we keep this network community together, that this represents a $20 per month customer service fee for being hooked up to the grid. As we add an additional 3,000 watts for electric vehicle driving, current gas costs at about $3 per gallon throughout much of the U.S. with a 30 mile per gallon, say, fleet average car versus something like the Ford Focus electric that I drive. There's a significant advantage to electric vehicles. Even though they do have a premium right now, that premium is going to disappear the same way it did for flat screen TVs. And the electric car costs currently about 2 to 3 cents per mile to drive with solar generated electricity. And it's about 10 to 12 cents per mile for a 30 mile per gallon, $3 per gallon gasoline. And so this represents the annual savings, about $600 per year by generating that with solar. And so that's these two cases. When we look at the 100-year life cycle cost, and this includes replacement costs. So in the economic section of zero, and again, you'd have to look to see the details, but I think I have windows replaced at 30 years, the HVAC system and water heating system at maybe 15 years or something like that, the ventilation system. So this has replacement costs built into it. But between the non-windowed and windowed case, the life cycle cost is maybe about $90,000, $80,000. And then these other cases, as we improve the house by sealing it, improve water heating, and optimal insulation, and then adding solar, we very definitely see a drop in life cycle cost. And with today's $3 per watt installed solar systems and using that to power about 12,000 miles per year in an electric car, it's a tremendous drop, about over $100,000 drop in life cycle costs. You know, why wouldn't a bank want you to build that? The finance side, you can also extract from zeros. And on the financial side, you know, it's pretty interesting because even though there's some fairly steep capital costs that you need to and can hopefully argue successfully with who's ever financing this, that we're talking about a conventional home that might have about, say, $1,530 monthly costs for mortgage, taxes, insurance, utility. These are representative of our costs here in central Illinois, so for sure California and the Northeast will be quite a bit different. But you can see that even adding expensive solar, $4.50 per watt installed, that we're really talking about $70 per month different to have a net zero energy house. And when we go over to today's solar costs and putting in enough so that you have electric driving, that the monthly cost, in fact, is less than what it would be in today's conventional home. Windows bump this up very significantly, so that marginal cost is quite high without significant benefit on utilities. But all of these others, a solar-powered house with fairly expensive solar, these are less than $100, less than your cable or your cell phone bill per month. The design day heating and cooling, these are given in zeros, and there's some interesting features here as we look at, say, a sunny winter day. These are using the 99.6 ASHRAE design day type conditions to calculate these, so similar to a manual J type calculation, and then a cloudy winter day. And we can see on a sunny design day, so for us, somewhat below 0 Fahrenheit is our design winter day. The windowed home, because even very, very high performance windows are poorly insulated walls, that if it's cloudy or nighttime, you've got, over here, you've got significantly higher loads than you do with a no windowed home. On the sunny day, it will balance that out and not penalize you much as far as the heating capacity needed. And as you seal and add a heat pump water heater, which does take you up a bit in the winter, and then finally insulating it more heavily, that you can see the drops in the heating capacity needed on a sunny day. And then, of course, a no windowed house has no difference between a sunny and a cloudy day, and that's reflected in this. But a windowed house, this is where your comfort is significantly affected by that. Over on the cooling, there a window that's not protected by external overhangs or external shading of some type. On a sunny summer design day, you're going from less than 1 ton of cooling capacity on a sunny day for this home to about 3 tons of cooling capacity. And then these other additions further improve the home. And here you can see that the heat pump water heater does drop the cooling load, not a huge amount, but you are getting the dual benefit of cooling with water heating. And in effect, and some of our studies have shown this analysis, the amount of heat that the heat pump water heater takes out of a house per day is equivalent to your metabolism, that is your heating effect on the home. So you as a 100-watt light bulb integrated over the course of 24 hours is roughly the amount of energy that's needed to pull out of the house and put into your hot water with the heat pump. And in effect, that just means that these heat pump water heaters are removing your metabolism, putting it in your hot water, and then getting it out of the house through the drain. On the latent, and we see that between, say, the conventional house and then sealing it up, and so the ceiling and then the number of people are the things that impact both the amount of humidity or moisture you might add in the winter, and in zeros where you specify both the indoor temperature and the humidity that's desirable. As you look through my settings in zeros, I've kept it at a minimum humidity of 20% during the winter, and this requires the addition of about 5 liters of water per day. You'll find that, and you can see online data for Equinox House. It's all online from our website for the last few years. So you can look at CO2, VOC levels as well as temperature and humidity, that we're somewhere around 40% humidity, and that's because of the cooking, along with we have a number of plants that there's enough moisture additions through showering plants and things that bumps it up. In the summer, we have to remove about 25 liters per day from this house, whether it was uncontrolled leaks of the conventional house or the sealed home that then has some type of ventilation exchanger. And that costs you energy, but not a significant amount as we look at it in perspective to the other energy uses. And then finally, as far as the number of people, as far as air quality, at 6 air changes per hour blower door test, that's roughly the level where you can get away with most people don't think your house stinks. It's not necessarily a very healthy level yet. And I set the ventilation schedule in zeros with the ventilation system so that it would have roughly the same ventilation performance as 6 ACH. So these reflect a 0.6 ACH house, a super sealed home like passive level, with ventilation then set at about 100 CFM overall, that kept the, and this is an output parameter in zeros, but that would keep the populace dissatisfied less than 20%, basically where ASHRAE ventilation standards are set to. And this shows the airflow. So we had a ventilation airflow of about 100 CFM in this super sealed home. A very small fraction of the airflow was uncontrolled infiltration, where the conventional home, all ventilation was through uncontrolled infiltration. And the problem with uncontrolled or a leaky home is that where the leaks are and where you live are 2 different things. So we find in more than 50% of the homes that that these are not healthy homes. Finally, on solar, I've already mentioned that we're modeling with $4.50 and $3 per watt. And to give you some idea of the physical size of this, on Equinox House, we put this 600 to 700 square foot solar system up on the berm, just so it would be more accessible for a few thousand people now that have toured our house. this is roughly the area. In our case, we put up 2,000 watts extra for electric car driving. So this much to power the home, this much for the car. And again, from zero's output, it shows that the 6 kilowatt system versus the 9 kilowatt system. A 6 kilowatt system in our area would be about 450 square feet, another 250 or so square feet to get up to 9 kilowatts for powering 12,000 miles of driving. And basically, you can look at it as the car bay square footage of your garage, roughly 250 square feet. That's enough in most locations throughout the U.S. to harvest enough energy for about 12,000 square miles of driving. And this just shows the solar power, nominal power difference for those. Finally, where I live, where I work is 100% solar powered. Yes, we do have excess in the summer and a need to supplement in the winter. But all of these transient storage issues, they're getting worked out, both the high frequency diurnal and cloudy day, sunny day with battery packs to other exciting changes that will be regional trading and other regional or seasonal uses of energy. Make hay when the sun shines in the summer, build extra refrigerators, TVs then, and then back off on that in the winter. But if this 4,500 square foot Morton building can be 100% solar powered, most any building can. So to end up, I hope you find Zeros to be a good design tool, and I hope you'll contact us with ways to improve it. Its overall goal is to save you time and to help you get to the answers so you can spend it where it's most needed, in the details of that design and in the construction and in the materials that you're going to select. I hope that this has given you a pathway and some ideas for how to avoid getting stuck and trying to figure out which way to go. That this path, whether you're in Florida or you're in the Northwest or Alaska, Wuhan, China, or Aachen, Germany, that when you put in the economics and the various choices, you'll still find that sealing it up using today's modern high-efficiency heat pumps to condition and to heat your water, and then to install solar, live on your daily allowance of solar energy, that you'll find that this is economically the path to take and financially will be beneficial. And I think our grandchildren will thank us for moving ourselves in this direction. So thank you very much. For those of you that have been able to hang in there, I'd be glad to answer any questions, and for sure feel free to contact us any time beyond this for any questions.
Hey, great. Thanks, Ty. I do see some questions coming in. We do have some more time, so please put in some more questions as you have them. And real quick before we get to those, thanks to all of our members, our board of directors, our volunteers, our sponsors, Sun Intuitive, Self-Tinting Glass, Build Equinox, GeoComfort, Niagara Conservation, Panasonic, and Certainty Air Renew formaldehyde eating drywall. Could not do it without their support. For those of you listening live, check your email, spam, take the survey, report your GBCI, we'll report your AIA. And those of you watching this in the future, on demand, not talking to any of you here right now, complete the 10-question quiz with an 80% passing rate. So, yeah, I do see some questions here, Ty. Kind of just going back to elaborate on some of your data there for a second. And so the one of them was on the cost per square foot. I understand, and I'm starting to understand that when someone says cost per square foot, it's not a black or white answer anymore these days. It means quite a bit. So when you say cost per square foot in this calculation, is that looking at the garage? Is it looking at the land? Or is it merely just looking at the living area of the house?
That's a good question. In the economic section of zeros, for example, and in those life cycle cost figures. So in our area, the cost per square foot of a house with a typical lot would run around $125 per square foot. And so in zeros on the economics, the stuff that's a fixed cost, you know, the land, the site work, and, you know, you're going to have a kitchen, you're going to have bathrooms and the furnishings and finishes. I have that in as $100 per square foot plan area of the house. And so the garage is coupled into that. So it's up to interpretation, and the main thing is for who's ever using it to know what they've assumed. Then, for example, the insulation, things like styrofoam or dense packed cellulose or stuff like that, I have assumed $5 per cubic foot for that material. So, for example, if a house had 1,000 square feet of wall area and the walls are a foot thick, then there'd be 1,000 cubic feet. And at $5 per cubic foot, whether somebody's using SIPs or ICF with styrofoam-like insulation or dense packed cellulose in some kind of, say, double-studded wall, $5 a square foot, $5 per cubic foot of insulation costs, and 1,000 cubic feet for a 1 foot thick wall, 1,000 square feet of that would be about $5,000 for that insulation. But then that gets mapped into the square footage of the house that's been assumed. So what you see in, say, that capital cost of the house was that there's about $2,000 for the house that is totally separate from those things that impact the energy and the air quality and comfort of the house. And then somewhere in the range of $25,000 to $50,000 that are for the heating and cooling system, the hot water system, the solar panels, the windows, the insulation levels.
Thanks,
I hope that.
Yeah. And there were a couple more questions here, kind of moving away a little bit from cost, but getting into life cycle. So I was going to kind of merge those two together. You know, the first one kind of, and we hear this one quite a bit when you're thinking long term. You know, we look at projects and we hope that they can last 200, 300, maybe even 1,000 years. So the question comes back, you know, 100-year life cycle, isn't that a bit of a long shot? You know, especially in the U.S. where people move often. And then on top of that, they were wondering about your, I think the slide before that in the mortgage section, they were wondering if you were referencing 15 or 30-year mortgages.
Yeah, great questions. On the life cycle costs, it seems most of our housing stock is assumed to have like 100-year lifetime. And to give you a rough estimate of it too, there's about 125 million residences. I think, you know, maybe 70% are single family homes and the rest then multifamily, but somewhere in that range. And it seems like about 1% or so per year is getting built, or about 1 million homes, plus or minus so much from 2008 when we were way down to now where things have rebounded a fair amount. But that lifetime, it's not, it's thinking beyond ourselves. And so thinking of 100-year construction, and maybe more like a mobile home might be 50-year assumption for its lifetime. And that's a significant impact in the cost analysis as well. But there's going to be multiple generations and multiple families, whether they're in it for 5 years, 50 years, or 100. But that life cycle cost really reflects that house moving through the years and the things that somebody at some point will have to replace. You know, somebody's going to get unlucky maybe, and each time they move into a house, they didn't notice that all the windows have to be replaced. And maybe somebody else is lucky in moving into a house where that doesn't have to happen. But this is beyond that personal, effect, but looking at the house more broadly. Now, in our lifecycle costs, and this is more just from being old and doing a lot of these analyses, we've avoided putting in, so this is a simple lifecycle cost without escalation, fuel, inflation, discount rates, things of that nature. And that's basically from seeing that over the years, even though we go through these periods where energy seems to be getting expensive or not as expensive, the fraction of money that you spend on a loaf of bread, the fraction of money that you spend on getting somewhere, on staying comfortable, a lot of those things have stayed pretty well within the same percentage of the income that families earn. And on that basis, that's in effect saying that trying to guess how things will inflate or escalate relative to one another, that's not so important. So we fix that, and that takes out a lot of confusion, because that's where you can make numbers lie in your direction by inflating this a little bit faster than that, or vice versa. As far as the financing, I think I have, well, it's a 20 or 30-year mortgage that's in there, but in the finance section, you put in the number of years, you put in the discount or the mortgage interest rate for that, and you put in a percentage of that house value that your real estate taxes are based on, as well as similarly your insurance rates. And so those are all in there, but as user-defined inputs. And so the numbers that I have in there, maybe 4% on the mortgage interest rate, and are reflective of what we see here, along with the real estate taxes.
Great, thanks, Ty. I had a question. Can this be utilized for multifamily or commercial buildings?
Yeah, very definitely. We do that all the time for folks, get them set up for using it on multifamily. You can actually do very large buildings. So the mechanical engineering building at the University of Illinois campus is getting ready to undergo a large renovation project. And a colleague of mine and myself were on the committee looking at the energy usages of the building. This is a 100,000 square foot building. 60 faculty offices, lots of classrooms and that. He did the simulation from an Energy Plus side of things, where he could do more detailed scheduling and large commercial system type modeling. I approached it from chopping each office, and so 60 off, times 60 for the number of offices, times 30 or 40 for the number of classrooms. But I could do each of those sections within zeros. So a south-facing office versus a north-facing. And similarly for multifamily, it's actually quite easy, because maybe 3, 4, or 5 of the walls or roof don't face the outside, and you just have a single exterior wall. And then everything else is just the same as being in a home, as far as the number of people, the hot water usage, the electric usage, how well you've assumed it to be sealed. And then whether that wall is facing northeast, south, or west, that you can do that. And what you'll find is that apartments really are quite super insulated, just from the standpoint that if you've eliminated 3, 4, or 5 exterior walls, you really don't have a lot of wall area that's communicating with the outside climatic conditions.
Yeah, exactly true. And then the last question I had, is there any, if someone is trying to use this and for whatever reason, maybe a code or a program, or just because they want to make sure they had done everything right, is there any kind of desktop review or quality assurance available, or that could be available or looked at in the future?
Yeah, while we haven't formally certified it through Best Test, and it's kind of at least as we've seen, it's somewhat confusing that as far as within DOE, who or how that actually happens. And if anyone out there is familiar with that, to maybe let us know. But as I mentioned, as far as the vetting of zeros, Luis Martinez's doctoral dissertation for sure will give anyone more than enough detail on the computational comparisons, which what's considered the gold standard for being able to model a home, and then our own empirical field-based studies. The Vermont is the most extensive, and from what I'm aware of, I haven't seen any other field study as the one that we conducted with Efficiency Vermont in the micro energy uses as well as the macro, the climatic energy uses, coupled with both comfort and air quality at the same time. And that is real world data that Zeros is compared with on a very fine grained basis.
Great. Well, hey, Ty, thanks for your time. Thanks for doing this. That seems to be all the questions we have. But you know, where can people find out more information about this or contact you if they have further questions?
I think right at our website, and then as I had in the presentation at buildequinox.com/zeros, that's where you can find the software. You won't find the software really, on our website, because we're not, say, advertising or promoting or pushing it out there. It's a tool that we've just made available to folks. So if you're having trouble finding that, just contact us at Build Equinox, and we can get you linked into that and then answer any questions. Overall, I just want as many solar homes as fast as possible designed and built throughout the country, and to make sure that these are places that are going to be healthy and comfortable too.
Great. Well, thanks to you, Ty. Thanks to Build Equinox. Take care. Have a great week, everyone.
Thank you. Bye-bye.